Alright, so this problem today is talking about the static equilibrium of a ladder resting against a wall. So if we look at the way the problem is set up, we have a ladder of mass M, big M sub L, length script L, leaning against a smooth wall, meaning that there's no friction right here against the wall. It makes an angle phi with the floor. The floor is rough so that the ladder does not slip. So obviously we're going to have a force of friction preventing the ladder from not slipping or sliding out. 3/4 of the way up on the ladder is a fireman or a painter or somebody with mass MF. So I guess we have a fireman on there. Now, rather than putting in a bunch of numbers, I'm just going to take you through how to set up the problem and how to create the conditions for static equilibrium with rotational forces and torques, and with the linear forces and using Newton's second law. So first thing you want to look at is setting up a free body diagram of the ladder. So the ladder is going to have a weight. So we have the weight of the ladder right here. I'll call it WL. That is acting downward. Put the floor in as a reference point. We're going to have a force of friction keeping the ladder from sliding out. So you're going to have a frictional force here. I'll call it little f. There's going to be a normal force from the floor. So I'll call it N sub floor with an F. From the wall, there's a normal force directed outward. I'll call that the normal force of the wall. And then 3/4 of the way up, I have the fireman who's standing on the ladder, and then there is going to be a weight of the fireman, and I'll call it W sub F. So this would set up all of the forces acting on the ladder, so we can look at our conditions for static equilibrium are going to be that the sum of the torques have to be equal to 0, and for translational equilibrium, the sum of the forces have to equal the mass times acceleration, which we know in this case is going to be equal to 0. So to set up the sum of the torques, first thing you have to do is select a pivot point. I can select the pivot point to be down here by the floor. My pivot point could be at the center. My pivot point could be at the wall. It doesn't really matter. It kind of depends on the problem as to where you select your pivot point. More than likely, at least to start, you want to select your pivot point that has the most forces acting on it in order to eliminate them out of the problem, because we know that if the line of action goes through the pivot point, it has no torque. So if I choose the floor to be my pivot point, then these forces, the frictional force and the normal force of the floor, do not create a torque. So I can write my torque equation from there. Now, given that I know that the angle here is phi, I'm going to treat this problem, rather than calculating moment arms, I'm just going to use the length of the ladder, since it's given as L, or L over 2 in this case. I'm just going to calculate what the normal component is of each of these forces and use that to solve for the sum of the torques. Because we know that we can solve for torque as the moment arm times the radial distance, which will have the sine theta in there. Moment arm times the force, or I can solve for it as just that lever arm times the perpendicular force. Either one of these numerically are going to be the same. So I'm going to choose to solve for it this way and solve for the perpendicular components. So my weight vector, my perpendicular component, is going to come down this way, and then there's a triangle right there. And we can see pretty clearly that this angle right here the ladder makes with the floor, that is going to be the common angle there. That will also be phi. Same thing for the weight of the fireman. I'm going to construct my components here, and then this is also going to be my angle that the ladder makes with the floor. For the normal force, it's going to have, that's my perpendicular component right there. I create my right angle right there. Then the angle that the floor makes with the floor is going to be equal to this angle right there, and you can go through the geometry to kind of figure that out and convince yourself that those are common angles. So now I've created what my perpendicular components are, at least visually. I can start writing the formula here. So I would take the weight of the ladder, this is going to be a cosine of phi, times L over 2, that's my distance. This one is also going to be in the same direction. So these would all be clockwise torques, so I'm going to make these all negative. That would be the weight of the fireman. Again, we're going to see a cosine of phi, and then that would be 3/4 of the length of the ladder. That would be the lever arm for that. And then finally, the normal force of the wall on the ladder is going to be a counterclockwise torque, so I'm going to make that positive, and I'm going to get the normal force of the wall, and then that is going to be the sine of phi times the length of the ladder L. So all of those torques adding up together are going to be equal to 0, and that would give me rotational equilibrium. So now I'll look at the translational equilibrium. Sum of the forces is equal to m times a, which is equal to 0. And all of my forces acting on the ladder must be equal to 0. So I know that the sum of the forces in the x direction, my frictional force, I'm going to make that positive going to the right, has to be equal to minus the normal force of the wall, has to be equal to 0. Those are my two x directions. And then the sum of the forces in the y direction, the normal force of the floor is going upwards, and then I would subtract the weight of the ladder minus the weight of the fireman. That has to be equal to 0. So I've set up several equations here. So we got this one, we've got this one, and we've got the one from the y direction. So now we have a system of 3 equations, and then again, depending on what you're given as part of the problem, you just use that information to solve for whatever you need to. Again, I could put my pivot point anywhere, so I could certainly write my sum of the torque equations up there, and that would give me, again, a little bit more complicated because both of these are exerting torques and they have components. It makes it a little more challenging. So again, picking the pivot point down there is what's going to make the most sense, at least for most of the problems that we're going to deal with.